Hello. In this quick video, I want to teach you about the basic principles of electromagnets, which are magnets that are not always magnetic. They're basically loops of wire that are turned on and off by electricity. So electricity and magnetism are linked on a fundamental level. These forces are actually different aspects of the same force. It's like it's wearing different masks. So electrical objects, they can affect the magnetic field. Specifically, the way that it works is that if you have an electric charge that moves from place to place, it creates a circular magnetic field around it as it moves. You can imagine it like sort of a magnetic tornado, a spinning vortex that follows these objects. Moving charge is called current, and I want to remind you really quickly about current. Current in a wire is what you get when charges move. Now, I just told you that when charges move, they make circular magnetic fields. And this means that there are circular magnetic fields around wires with electricity moving through them, no matter what these wires are powering. So technically, every single wire is sort of an electromagnet because they all create little magnetic fields, but they're not very strong. To figure out which direction these magnetic field vectors point, we use something called the right-hand rule. Basically, the way it works is, imagine you have a wire, okay? And the electricity is running this way in the wire. You stick your thumb in the direction of the current on your right hand. Then you curl your fingers around. So the current's going this way. I put my thumb this way, and I wrap my fingers around. It's probably easy to see this way. So this is the direction the current's moving. I point my thumb in the direction the current's moving, and I wrap my fingers around like that. I curl my fingers. The direction that my fingers moves is the direction of the magnetic field at that point. So facing the camera, my fingers are curling down. The vector here points down, but this way, it points up. So on this side, the field is going up. As an example, which direction would the magnetic field be moving in around this wire? Well, pointing in. Would it be going this way or this way? Well, stick your thumb in the direction of the current and curl your fingers. If you do that, you'll see that on the left side of that wire, it should be coming out of the screen, and on the right side of the wire, it should be going into the screen. Kind of like this. This will tell you the direction of the magnetic field lines around this wire. So here's another thought experiment. Let's say I have current running through a wire, and it's creating a circular magnetic field. Now in the middle, right there, between the two wires, you can see that the arrow is going into the screen. So if I want to strengthen this magnetic field and make another arrow also go into the screen, which direction should that second wire have its current be flowing in? Should it be going up or down? And you can do the right-hand rule, but if you want the magnetic field to be pointing in the same direction, then that means you want the arrow to be going into the screen on the right there. And so that means that you're going to want the current to be moving down, because according to the right-hand rule, when the current's going down, the arrow goes into the screen. But do you really need to use two wires? I mean, you can if you want to. But if you imagine flowing electricity as flowing water, if I wanted to go up here and down here, I could just connect the two, right? I can connect the two pipes. So if you take this wire and you sort of loop it around on itself, this single current causes these reinforcing magnetic fields in the middle. You can have one that doubles back. But why would you stop at a U-turn? I mean, if you loop it around again, you can get more magnetism. And if you loop it around again, you can get more magnetism. You just keep creating these loops, which keeps creating these magnetic fields pointing in the same direction. And this is actually what an electromagnet is. You get an electromagnet if you take a wire and you loop it around a bunch of times. That's it. Looped up wire. The magnetic fields created by the current will reinforce each other in the middle, and so it gets very strong. So an electromagnet is just a wire with a bunch of loops. When the electricity moves through the loops, you get the magnetic field. These are all different examples of magnetic fields inside electromagnets. Now, if you have more loops, you get a stronger field. And if you have a stronger current, you have a stronger field too. You can put in a metal core, and that will make these electromagnets even stronger. So virtually every electromagnet used in the modern world has a piece of iron put in the middle. You can visualize the field of an electromagnet by scattering iron filings around and then seeing what happens. The magnetic iron filings will arrange themselves in order. And you can see here, this is the electromagnet's off. So I'm looking at this picture. The electromagnet is off, but then when it turns on, you can see the loops that form. You can turn electromagnets on and off at will, so you don't have to be as careful about them. You can control the strength of the magnet by controlling the current, which is really useful. And you can also control the strength by changing the number of loops. So if you want to pick up a car, you want a lot of loops. And if you want to pick up a paperclip, you don't want as many. So electromagnets are like normal magnets, except they're more useful because we can control them better by altering the electric field and the number of loops. That's it. It was a really short primer on electromagnets. I hope it was helpful.